Our next speaker will be Taishi Kawamoto from YITP, and he will tell us about finite size scaling of ETH in AdS CFT.
Yeah, thank you for introduction. I'm Taishi Kawamoto from YITP in Kyoto, and I appreciate the organizer to give me a chance to long talk in this nice conference. And today, I'd like to talk about my recent work. It will be appeared in archive in this month about ETH in AdS CFT, and with that. The question is, in statistical physics, is for given complicated systems and given initial state, can we observe some equilibration and summarization? And it is known that the sufficient condition for this question is called some condition eigenstate summarization hypothesis, short for ETH. And for chaotic system, we expect that we can prove this condition ETH. And indeed, for random Hamiltonian, we can prove the ETH. And my question in this talk is, can we prove the strong ETH in the given single Hamiltonian? And especially for AdS CFT, the gravitational collapse corresponds to some summarization process in the boundary conformal field theory. And in the general relativity perspective, some massive objects should be collapsed to some heavy black hole states, and this should be for any heavy object. And we expect that the ETH should be for the holographic CFTs. And this is some contents of today's talk. And first, I review some what is the ETH, and next, I introduce my recent work, and so start some review of eigenstate summarization hypothesis. And firstly, I want to fix some notation in this talk. So if we write down some energy, this is the energy of the energy shell we fix, and this is a subset of the total Hamiltonian. And if we denote D, this is a dimension of this energy shell, and microcanonical entropy is just a logarithm of this dimension. And if we write down some bracket of MC, then this is an expression value in this microcanonical ensemble of this energy shell. And also we have some unitary time evolution with some single Hamiltonian. And the Cn is some coefficient for the some initial set psi 0 in the energy eigenstate basis. And this overline T denotes some infinite long time average. And to start with discuss on ETH, we need to define the thermal equilibrium. And in the context of black hole thermodynamics or AdS CFT, we should notice that there are serial definitions of thermal equilibrium. And this thermal equilibrium is a set of the thermal limit and the operator we want to observe. And for example, there is some two kinds of thermal limits. So one is a large volume limit, which typically appears in the statistical physics. And also for AdS CFT or some gravitational context, we have some larger limit or some semi-classical limit. And also we should choose a set of the observable operators, which is relevant in this thermal limit. And for the large volume limit case, we have, for example, some this A is a set of some macroscopic observable like some total magnetization in the spin chain or some energy flow and etc. Or in quantum system, sometimes we take this A is a set of all of the some local operators or a few body operators. And for the second, this larger limit case, it is natural to take this A is some kind of some right or right single or multi-choice operators. And with this thermal equilibrium, we next define some notion that pure states are in some thermal equilibrium. And here we define that some pure state psi in the energy shell represents some thermal equilibrium with respect to some thermal equilibrium is. So it holds that for any operator in A, the expression value of this psi is very close to some microcanonical one, up to some exponential of the entropy error. And next, I want to define the notion of equilibration. And we say that the initial state psi 0 shows some equilibration, like this relaxing. And this is defined that it holds that for any operator in A, the long time average of the fluctuation here is actually very, very small, like some exponential of the entropy. And thus equilibration is a relaxation to some steady state, and which is not necessary to be some microcanonical ensemble. But there is some steady state, and the fluctuation around this state is very, very small. And next, I want to define the notion of the thermalization. And the definition is follows. We say that initial state psi 0 in energy shell shows some thermalization. It's defined that it holds that for any operator or in A, the long time average of this expression value in psi t is close to one of the microcanonical ensemble. So this says that this thermalization is that some steady state, which is guaranteed by some equilibration its whole, is actually some equilibrium state like microcanonical ensemble. And for this definition, we can say about some dynamics. And importantly, we can show that most of the some quantum state in the energy shell, like this green region, represents some thermal equilibrium in some sense. And for example, if we take some A is some set of some local operator, then there is some theorem called some canonical typicality, which states that most of the pure state in energy shell is actually close to some microcanonical ensemble. And so this kind of some typicality theorem, we have some paradigm that the equilibrium state is actually some typical state in this very, very large region in energy shell, and also non-equilibrium state is this small atypical states. And we naively expect that if we start from this non-equilibrium state at atypical non-equilibrium state, and after some complex evolution like this one, the state reacts to some typical equilibrium states. But the typicality theorem itself is holds for any quantum mechanics in large degrees of freedom, and it is just a kinematical statement. And it is not trivial that this kind of equilibration and thermalization really happens in the given Hamiltonian. And thus, it seems that we need some condition that it depends on some theory and initial states, and which guarantee us that some equilibration and thermalization. And this is actually some ETH I introduced from now. And the ETH is composed of these two conditions. One is for any operator O in A, and for any energy eigenstate En, the matrix element in the energy eigenstate basis, and the off-diagonal component is very, very exponentially small. And the second condition is that the diagonal part is actually very close to some microcanonical ensemble. And if this condition is satisfied for given theory, then we can show that off-diagonal ETH means and the non-resonance condition, which I mention later, these are some equilibration from any initial states. And also, if we have some diagonal ETH, then we can show that the thermalization from any initial states. And for example, I want to give us some proof for equilibration if we assume some off-diagonal ETH and some non-resonance condition. And the non-resonance condition is condition like some the level difference of energy eigenstate is same, then this N and L is same, and M and K equal to same. And this is expected for a chaotic system, and one simple counter example is just harmonic oscillator or free theory. And if we assume this non-resonant condition of diagonal ETH, we can show that some long time fluctuation of the time evolution is actually bounded by this off-diagonal component of some matrix element, and this is very, very small because of this off-diagonal ETH. And we can do similar things for summarization. And this is some introduction of some ETH for very generic quantum mechanical system. And next, I want to explain how to prove ETH. And there are some several ways to prove ETH. One is some diagonal, exact diagonalization for Hamiltonian and doing some numerical computation. And this is done for some spin chain like Harvard model or so on. Or maybe we consider some random matrix theory or some random Hamiltonian, and we can show some typical Hamiltonian, show some ETH. And the question is that for given some single chaotic Hamiltonian, and naively speaking, it seems that we need to know all of the energy spectrum and energy eigenstate and compute any matrix elements. But this is definitely a hard task. And here we take some another strategy. And to this end, consider some statistics of some energy eigenstate in the energy shell. For example, so we consider a set of the energy eigenstates, I denote some Pascal E in the energy shell, and consider some of the statics of this energy eigenstate. And one important inequality is following that for any positive real epsilon and for any bounded operator O and for any non-degenerate Hamiltonian and for any initial state psi 0 in the energy shell, we can show that the difference of the long time average and the microcanonical ensemble is bounded by this quantity. And the point of this combination is the square root, and this D is some dimension of the energy shell. And the new things is this two quantity. One is for some effective dimension, which is defined through this initial state and express some number of the energy eigenstate contribute to some initial state. For example, if we take some psi 0 is just some one energy eigenstate, this effective dimension is just one. And this is just clearly some initial state dependent part. And the another ingredient is this delta epsilon ETH, and this is defined this probability. And this probability is defined on this set of the energy eigenstate, and we consider some uniform distribution on this sets of energy eigenstate. And this delta represents the probability of this EN is highly deviate from this microcanonical ensemble expression value. And this is actually some represents a number of the some quantum scar states in the given Hamiltonian. And this is highly theory dependent part. So this inequality is very, very nice because the contribution from initial state and the contribution from the theory dependent part is completely factorized in this way. And then, if theory and the initial state satisfy this inequality, that is, this combination is very, very small in the order of the exponential of order microcanonical entropy, then we can show that the summarization from this specific initial state. And moreover, if the theory satisfies this inequality, then so this is the effective dimension is 1. then we can show that this theory satisfies some diagonal ETH. For example, if we put this psi 0 is just single large eigenset, then the right-hand side is appeared in the diagonal ETH, and this is exponentially small if we take the epsilon to be small. And there is some interesting conjecture in the statistical physical community that is for integral system, this probability delta ETH, which is some probability, is exponentially small. And this condition is called some weak ETH, and this is valid for most of the quantum, most of the some Hamiltonian. And if this is true, and we have some large effective dimension, then we can show that the initial state is summarized. But for non-integral system, the scaling is drastically different from integral one. That is, this delta ETHO is actually doubly exponential small for the microcanonical entropy. And if this is true, then this inequality is trivially true, and we have some strong ETH. And this is a conjecture about there is some numerical computation, like for some spin chain, some chaotic spin chain, and this is verified in such as some numerical computations. And also we have some similar story for off-diagonal part or some equilibration part. And that is for any positive epsilon, and for any bounded operator O, and for any non-degenerate and non-resonant Hamiltonian, and for any energy eigenstate, we have that the fluctuation, long time average of the fluctuation is bounded by following, and there's some new quantity here, delta of diagonal ETH, which is some probability on the set of the energy eigenstate violates the sum of diagonal ETH. And yeah, almost parallel to the summarization case, if the theory and state satisfy this inequality, then we can show some summarization from any initial state. And if the theory satisfies this kind of some double exponential suppression, then we can show the of diagonal ETH. And so far, I discussed some very general argument which valid for any quantum mechanical system. But my interest is holographic CFTs. And we know that some holographic CFT is maximally chaotic in some energy band. And also some intuition from some general relativity, we expect that some holographic CFT satisfy strong ETH, and this means that the holographic CFT shows some doubly exponential scaling. And I want to fix some definition of summary equilibrium. And here we take some large L limit as some thermodynamic limit, and also take some relevant operator is some single trace operator or some few multi-trace right operator. And bulk theory is some Einstein gravity plus matter on AdS spacetime, which is called some bottom-up construction for AdS CFT. And so this is my recent discussion and proving double exponential scaling in the AdS CFT. And to this end, I want to explain some sufficient condition for double exponential scaling. And actually, if the theory satisfies two non-trivial conditions, which is valid for some chaotic system, then we can show some double exponential scalings. And to this end, we need to introduce some important quantity that's a thermal canonical Weightman function with this this definition. And this this O is some one-point subtract operator. And if the theory satisfies these two conditions, then we can show double exponential scaling. And one is some quantum mixing property, that is a long time average of 2-point function is exponentially suppressed. And the another condition is called some clustering property, which is that a long time average for 2p thermal canonical Whiteman function is bounded by some product of the long time average of 2-point function. And next, I want to explain why these two conditions lead some double exponential scaling and strong ETH. And the mathematical ingredient is called some sub-Gaussian property. And the sub-Gaussian property is a property for the some probability distribution, and this is one specific example of some large deviation theory. And the definition is that a random variable x is called some sigma sub-Gaussian if the probability, sorry, there's a typo, this x minus expression value of x is larger than some epsilon, is bounded by some Gaussian with variance sigma, and the random variable x is sub-Gaussian. Is actually there some equivalent condition that LP null is bounded by some this variance for any even even p larger than 2. And and I want to involve this property to the for example this probability. And to this end, we need to elaborate some of the moment of this probability. And for example, some expression value of this probability is just some expression value of some microcanonical ensemble. And the piece moment is a little bit complicated, but after writing down some definition of this expression value, we have this equation, and we can rewrite this product of some matrix element in this form. And if we assume some Hamiltonian is non-degenerate, then this canonical delta can be written as some this kind of some Fourier transformation, and we can rewrite this En is just Hamiltonian, and we can insert this into every canonical delta. We obtain that this piece moment is just some product of time evolved some matrix element, and we can rewrite this one in simply some microcanonical ensemble, and then we obtain that this piece moment is actually some infinite long time average of the piece order of some microcanonical some Whiteman function. And as a some general story for statistical physics, the microcanonical correlation function is bounded above by some canonical thermal correlators. And if we assume some this clustering property for this canonical ensemble, then this moment, piece order of moment is bounded by this 2-point long time average of 2-point function. And there's some general story of sub-Gaussian property. We can prove that this probability is bounded by this 1 over long time average of 2-point function. And if the theory satisfies this mixing property, that is this 2-point long time average of 2-point function is exponentially suppressed, then we have some double exponential scaling. And And the key point is that this clustering property and this mixing property, which is highly non-trivial. And next, I want to explain that actually bottom-up AdS CFT have this clustering property and mixing property. And firstly, I want to explain some mixing property, which is already known from some 20 years ago. That is in AdS CFT correspondence and beyond the Hawking phase transition, the canonical two-point function has this form. That is, we have some collision function computed from some the BTG black hole or some just black hole, and there is a non-partitive correction for this two-point function. That is, for example, thermal AdS. The two-point function computed from some thermal AdS, and maybe there is another subtle point. And as some simple calculation, the prefactor is just some exponential of some order 1 over g Newton, and this is exponential minus order 1 order of micromechanical entropy. And for AdS3 case, we know some concrete form of the two-point function. And for BTG black hole case, we have some hyperbolic cosine dependence. But some AdS case, we have some cosine dependence for time. And this black hole part has some rate time decaying like this one, exponential decaying, and this means that this exponential decay means that the long-term average is actually 0. And thus we have some mixing property. And this mixing property is actually coming from some structure of some black hole horizon, because we know that some wedge theory have some quasi-normal mode, or in other words, this mixing property is coming from that some UV divergence in this QFT on this wedge. And in recent terminology, this is same as that this wedge, and QFT on this wedge have some type 3-1 von Neumann algebra in some larger limit. And this mixing property is also related to some information paradox, because that this mixing means that there is no Poincare recurrence, and actually the information for the initial state is lost. So in summary, this mixing property is coming from black hole horizon, and holds for any high dimension or any kind of some black hole. So this I explained some specific example in BTG black hole in 3 dimensions, but this discussion is very, very general. And the one most non-trivial point is this clustering property, and this can be proven, for example, if we assume some generalized free approximation, which is equivalent to some ignoring some any 1 over n correction. And for example, some 2p point thermal Whiteman function and conscious some long time average, and because some generalized free approximation, we can use some weak contraction, and thus this 2p point function is just some product, sum of the some product of this 2-point function. And because we have some long time average, this time dependent is not important, and we can have just some we can just multiply some number of the weak contraction. This is some double factorial of 2p minus 1, and we also have some p times of the long time average of 2-point function. And this double factorial is upper bounded by just p factorial, and just we have some clustering property for this generalized free case. But this example is highly trivial since even though we don't have this long-term average, we have this factorization. But the point is that in chaotic system, we expect that we expect this clustering property, but we do not expect some clustering property just for this thermal Whiteman function itself. The statement is just for this long-time average correlation function. And okay, so the summarize. So this mixing property and this clustering properties fall in generalized Fourier application, and this leads that some boundary holographic theory satisfies this strong ETH. And the point, and but this, as I mentioned, this generalized Fourier approximation is highly trivial, and I want to add some one-over-n correction. My statement is that even though we add this one-over-n correction, we can prove some clustering property. For example, we consider some p equal 2 case, and this is just a 4-point function. And because of this one-over-n correction, we have some connected green function, and this is related to this Witten diagram. And we also consider some bulk to boundary propagator, and we expect that this mixing for this bulk to boundary propagator like some green function in the boundary theory, and we expect the boundary bulk to boundary propagator have this form, and even though we add some one-over-n correction in partitive sense, we see that this mixing property is not changes, but this one-over-n correction just makes some conformal dimension is replaced some renormalized one, or there is some additional partitive correction. But we can show that this first part satisfies this this condition, and in total we have some mixing property for this bulk to boundary propagator. And then we can show that the long-time average of this 4-point function is actually the product of this long-time average of bulk to boundary propagator. And because of this this mixing property for this first black hole part, we can just replace some long-term average for this thermal radius part times some exponential suppressed term. And for example, for tree diagram case, just this u is coupling constant times the delta function. Then we have this form, and this factor is just the fourth order of this long-term average of 2-point function, and this is exponentially small to the disconnected part for the 4-point contribution. And this means that in the long-term average, this one-over-n correction is highly suppressed, and we have some same result of some generalized free case, and we have just clustering property. And the another problem that when we take P is very, very huge, like some order n square, then we cannot believe the picture of the effective field theory on the black hole, and we want to seriously take into account some back reaction with the gravity. And this is a highly heuristic argument that but this is a heuristic argument, but it seems that we can conclude the clustering property for this big order. And for example, if we consider this 2p-point function and take some first two time, it's very, very huge compared to the other, and consider this first two operator is just some proof, prove operator, and the other is a kind of some shock wave like this yellow region, then it is nice to expect that this 2p point function is factorized to some 2-point function on this background and the canonical 2p minus 2-point function. And if we do some smearing some operator in for spatial region, spatial direction, and doing some computation, we can show that this shock wave geometry is kind of some Bayesian geometry, and we just need some long-term average, and we expect that this Bayesian geometry is related to some static black hole in some temperature beta prime, and we know that some long-term average of some black hole background 2-point function is exponential suppressed, and we can do some, we can have some clustering of this 2p point function is some product of this exponential suppressed part times a 2p minus 2-point function. And if we do some recursively do this algorithm, we have some clustering in this, even in this order. But this explanation is highly heuristic, and we need to do some robust proof. And maybe time is very early, but I want to summarize my talk. And the some structure of some black hole and some structure of bottom-up AdS CFT correspondence show that some quantum mixing property and some clustering property for some thermal canonical Whiteman function, and this means that some double exponential scaling, and this is equivalent to some strong ETH, and this strong ETH is leads some summarization and equilibration, and we find that some general field theory on black holes shows some this strong ETH in dual theories, and also if we add some one-over-n correction, the long-term average structure is same as this general free field theory, and we have just some bottom-up holographic field theory is shows some strong ETH, and we can also show some off-diagonal ETH part in almost parallel ways, like we have some this kind of property, and we can rewrite some probability for off-diagonal probability in terms of canonical Whiteman function, and we have some double exponential suppress for the probability, and we have some off-diagonal ETH. And the future direction is that we want to apply this discussion for more realistic holographic QFTs, which is like some n equal 4 pyramids or some ABJ theory, which have some string dual. And here I do not consider some effect of some giant gravity expansion or some brain-like contribution in the thermal correlators, and also I assume some non-degeneracy and non-resonance condition, which is violated if we add some symmetry like supersymmetry. And I think that if we lose some condition like non-degeneracy and non-resonance condition, we have some almost parallel story. But there is some discussion like there is some quantum scarce state in holographic TFTs, and I do not know how my story and this, that kind of scarce story is consistent or not. Yeah, this is my talk. Thank you for listening.
Yeah, usually ETH is written as a, the diagonal part plus the off-diagonal part, and off-diagonal looks like e to the power s half minus s half f, and there's a f function, smooth function.
Yeah, maybe some usual form.
Yeah.
Yeah, we can rewrite.
Yes, diagonal is okay. Off-diagonal goes like.
Diagonal part is some microcanonical ensemble. Plus some correction is disorder, and the off-diagonal part is correction of disorder.
Okay. That off-diagonal, okay. Sorry. off diagonal, actually the statement is that it has, yeah, actually in both sides, on the right hand side, it has to be e to the power minus s half. So can you?
You care about this coefficient here?
Yes. So what I'm saying is, can you make it more precise? Like, well, according to ETH, it has to be s half.
Yeah. For example, for random matrix theory, show that this is actually 1/2 times entropy.
Yes. Yes.
But I don't sure that like in my proof we have some for given some Hamiltonian we can prove this is 1/2 or not.
Okay. Yeah, and another question is, this f function, this off-diagonal f function, it actually controls the 2-point functions, right? If you want autocorrelation function, t, this time difference, okay, 2-point functions, okay. So f function, it has a lot of information, okay. But in your case, when you're doing just time average thermalization, the information of the f, okay. You're not keeping track of the information of the f. Okay, of course it will be suppressed by e to the power minus s, but that f function is actually although it's very suppressed, it controls 2-point functions. Okay. And higher point functions.
Actually, in my definition of this kind of some equilibration summation, I just care about some operator. And I don't care about the 2-point function. Of course, we have some implication for 2-point function, right?
Yes. Yeah, I mean, what I meant to say is the f function has more information. I mean, you cannot just ignore it for now. Of course, this is first step. Okay.
But in this definition, just care about the order. You're right.
Any other question? Okay. If not, let's thank.
Thank you.